Well, trilogies are really the perfect format for a saga. Sagas should end after 3, we all know that. But when the third and final installment is a really big success, it's really hard for a creator to say goodbye. The third video in my series on hypothesis testing got 2 views, which is twice my average and 2 more than many of my videos. So that makes it my big hit. So to capitalize and see if I can get 2 more views, I'm actually going to carry this saga into a 4th in the trilogy. I'll make the explosions bigger in this one to make up for the stale writing, bad acting, and predictable plot line. Alright, so in our previous examples of hypothesis testing, we were using coin flipping, and in the case of 1, 2, or 3 flips, we would write out the whole sample space. But how can we know the whole sample space of an experiment where the outcome variable is a continuous variable? For example, suppose I'm measuring income in dollars, or how tall plants get, or how long it takes people to finish running a race. How can I possibly know beforehand all the possible outcomes of an experiment like that? Well, it turns out that for many variables, it's actually not that hard. It's our good old friend the normal distribution, or a distribution very close to it, the t-distribution. So let's start with this normal distribution here. You see just a normal distribution. This is not the standard normal distribution. You can see there that oh, there's my laser pointer. Okay, you can see there that the mean is not 0, so this is not the standard normal, and so that means the values here on the x-axis are probably not standard deviations. It really doesn't matter what that value is on the x-axis for this example. Just, you know, it's whatever we've measured. And so whatever we've measured has a mean of about 31, and most of the observations fall close to the mean, with a very few that are really small and a very few that are really big. Alright, so suppose this is my population. Suppose I take a random sample from this population. Random samples don't really exist for any interesting population, as I have argued in another video. I think they're mythical. But let's pretend that we could actually take a random sample from an interesting population. Or pretend that this is not a very interesting population, like let's say it's all of the students at one particular school, which is not terribly interesting. Students is an interesting population, but all the students at one school, not terribly interesting. All the doctors at one hospital, not very interesting. Doctors in general, interesting population. Nurses in general, interesting population. All of those at one particular hospital, only really interesting to the hospital administration at that hospital. Not terribly interesting for science, because they don't represent doctors in general or nurses in general, and so on. But let's suppose that we could do this and take a random sample. So the first person, or pigeon, or rat, or whatever it is that I'm studying, that I'm going to sample, could be this person, or this observation. So something around 38, 39, somewhere around there. And the next one is maybe around 16. And so I just keep doing this, selecting at random out of this population. And eventually I get a sample. And that sample has a sample mean, x bar. And the sample mean is an estimate of the population mean, which we represent with Greek letter mu, right? So x bar here is an estimate of mu. But x bar does not exactly equal mu. However, the only cause of the difference between x bar and mu, between the sample mean and the population mean, is just chance, right? Because I was randomly sampling from this population. So just by chance, the way I've illustrated it in this example, I just happened to get observations just a tiny bit over in this left side of the population distribution, not quite as much over here on the right side, and so my mean's a little bit of an underestimate of the population parameter mean, but it's only chance that caused that difference. Now suppose I take another random sample from the same population and calculate the sample mean. The new mean is also an estimate of the population parameter mean, mu, but once again the sample mean is not exactly equal, or doesn't have exactly the same value as mu. But again, the only cause of the difference between x bar and mu is chance. Also, note that x bar 1 is not the same as x bar 2. And in the same way, the only cause of the difference between them is chance, also called sampling error. Now, I've drawn it in an exaggerated way here so that the differences are clear, but in reality, of course, if we are randomly fishing two samples out of the same population, the differences between the sample means and the population mean that they estimate, and between each other, will be small most of the time, and only very rarely will we get big differences between the two sample means just by chance. So now let's consider a different situation. Let's say there are two different populations, and we're going to take a random sample, one random sample, out of each one of them. What makes two populations different from each other? Well, just a different value for one or more population parameters, and as I've illustrated it here, the mean, right? We have two different population parameter means, and so that makes these two different populations. All right, anyway, so let's take our samples. Once again, the sample means are not exactly equal to the population parameter means that they estimate, but the only cause of the difference is chance. Pure luck, just sampling error, randomness. But notice that there is now another cause of the difference between the sample means themselves. X bar 1 and X bar 2 are different from each other owing to chance, but also because they came from different populations, because the data were drawn from two different populations. The different population means cause a difference, cause part of the difference, I should say it that way, cause part of the difference between the two sample means. So now, these sample means we would not expect to be close to each other most of the time. We would expect them to be only as close as the population means from the populations that they came from on average over the long run. Now, occasionally, we could draw two different samples out of these two different populations, and they could actually be exactly the same. You see here that there is some overlap between the distributions, so we could certainly get sample means. There's actually, well, I should have drawn that. I should have pointed that out here with the population distributions. There's quite a bit of overlap between the population distributions, so it's quite conceivable that I would actually get a bigger sample mean out of population 2 than out of population 1. That could happen by chance, right? All right, but anyway, the main point is there's now a systematic difference between these sample means, not just chance. So, let's say I have done an experiment where I have an independent variable that might or might not cause a difference in my dependent variable. And just to make it concrete, let's just make up an example. Let's say I've given a drug to one group and a placebo pill to the other group, and I've measured depression. I think maybe this drug is going to be a good antidepressant, so I'm going to give it to one group of people to see if it relieves their depression. Another group gets a placebo that looks exactly the same, but it doesn't have the active ingredient of the drug in it. And I want to know if this drug reduces depression compared to the placebo. So the x-axis in this example would be depression. So now I've given this a concrete meaning. This would be depression. And this one would be depression. Here's my population up here, and my single population if there's no difference. Well, I'm getting ahead of myself. All right, so the x-axis is depression, but you can imagine it as any variable you want. So if the drug does not work, then that means that the mean level of depression is the same for both groups. Or in other words, my two groups can be thought of as two samples from the same population as far as depression is concerned. Why the same? Because it's the population of people with that mean level of depression. But if the drug works, what that means is that I'm in the two population situation, because the drug is causing different values for depression. So if the drug works and it alleviates depression, then this red distribution here, this one here, would represent the people who got the drug. This blue one would represent the people who got the placebo. And we would be in this situation rather than in this situation. So how can I figure out which situation I'm in? Well, we need to go back to that one population situation. I need to know what are all the possible outcomes of taking two random samples from the same population and calculating the difference between the sample means. Remember from probability that that's called the sample space, right? So I need the sample space of this experiment. And it turns out that all of the possible ways that experiment could turn out follows a distribution that is very similar to the normal distribution, just a little bit fatter in the tails and flatter in the middle, called the t distribution. And here's the formula. This particular one is called the independent samples t, or t-test for independent samples, or t-test for independent groups. Man, you just got to love how there's so many different names for all these tests. I think every textbook writer must come up with their own name. Maybe it's a copyright thing. I don't know. Now, back to my experiment. The null hypothesis here, represented right here. Remember, we represent the null hypothesis with h sub 0. We pronounce that h naught. We do that because we want to sound British and sophisticated. So h naught is that mu sub 1 is equal to mu sub 2, or in other words, I am estimating the same population parameter mean with both of my sample means. In other words, I am in this situation here where there's just this one population mean, and mu sub 1 and mu sub 2 both go here. My experimental hypothesis, h sub 1, also called the alternative hypothesis, the research hypothesis, that one also has a million different names, is simply that these two means are not equal to each other, or in other words, that I am in this situation right here. So, if this new antidepressant drug does nothing, then the difference between my two groups, the drug group and the placebo group, will follow a t distribution. So I can calculate the t statistic, which is what this formula is right here. We're not going to do the example in this video. I'll do another example, another video with a completely worked hand computation example, and I think I've already uploaded a video actually on how to do it in SPSS. I think I still need to work on the one how to do it in Excel. Eventually I'll get around to R and SAS and all those. Anyway, so moving on. If this drug does nothing, then the difference between my two groups, the drug group and the placebo group, will follow the t distribution. So I can calculate the t statistic and then figure out from the t distribution the probability of getting a t that extreme or even more extreme just by chance, however extreme of a t statistic I get. Remember from the hypothesis testing video that that's called the p-value. If the p-value is lower than alpha, which is usually around 0.05, that would mean that I would very rarely get such a big mean difference if I'm in that top situation, sampling from a single population. I can reject the null hypothesis. Whether I can then conclude that the drug caused the change in depression depends on how well I've designed my experiment. Remember, no statistic implies causation. Most of you have probably heard correlation does not imply causation. Well, it's actually no statistic implies causation. Experimental design implies causation. So if I randomly assigned people to groups, and if I kept everyone blind to which group they were in so that I don't accidentally or on purpose, or accidentally on purpose, treat one group different than another group, then I can conclude that the drug caused the difference. There's simply no plausible third variable alternative explanation. The only alternative explanation is chance, right? I mean, it's possible even with random assignment. Maybe I just got all the happy people under the red distribution and all the sad people under the blue distribution. That can happen under random assignment. The p-value that I get is the probability that something like that would happen, right? That is what the p-value is expressing, is the likelihood of basically a failure of random assignment or something like that. Something is different between these groups just by chance. All right. All right. If there is a third variable that might confound the study, like if the experimenters knew that these folks had gotten the new experimental drug and that these folks had gotten the placebo, maybe the experimenters were just being extra nice to these folks and maybe being a little bit cold to these folks, and maybe even doing that subconsciously. It may not be a fraud, right? It's not that I'm necessarily trying to make the experiment come out a certain way. I may subconsciously, if I really believe that this drug is going to work, I might just subconsciously be happier around these people as the experimenter, right? Because I'm sure their depression is going to be alleviated. And when I'm around these folks, I know they're on placebo, and I treat them sadly, because I know that their depression is not going to be alleviated, or it's going to be alleviated only by the placebo effect, that sort of thing. All right, so anyway, if there is a plausible third variable, then I really shouldn't be making a causal inference. All right, so anyway, that's it for the independent samples t-test in a nutshell. That's conceptual, of course. We didn't get into the practicalities of how to calculate this darn thing. But just to sum up, our null hypothesis, we represent it h naught mu1 equal to mu2, and we can say that in everyday language as both sample means estimate the same population parameter mean. The experimental hypothesis, H1, mu1 is not equal to mu2. That just said in everyday language, the sample means estimate different population parameter means, or in other words, there is a non-random difference between the groups that these samples were taken from. And you use this t-test. This is called, did I mention this? I may not have mentioned this. This is called the independent samples t-test. Oh, I did mention it. Yeah, when I talked about multiple names. All right, so you use the independent sample t-test when you have two groups, in other words, two samples, and you want to know if the means of the samples are different from each other. All right, that is plenty long enough.